The rate at which work gets done is called power. And the formula for finding average power is work over time, which is equal to energy transformed over time. In the global SI system, power is measured as joules over seconds, and joules over seconds is equal to a special unit of measurement called the watt, which is denoted with W. Now, before we start solving problems involving power, let me explain to you the difference between energy and power. So a person can jog quite far before too much energy has been used. But a person sprinting, so he's going way faster, he gets tired way earlier. This is because their body, in this case, is held back by power, which is the rate of him converting energy, specifically chemical energy, like calories, into mechanical energy. So at the start of these two scenarios, he might have the same amount of chemical energy in his body or energy in his muscles. But the guy sprinting has to stop way earlier because of the rate of work, which is power. Let's go through a problem. Imagine for a second that you're a parkour athlete and you want to test your explosive power by sprinting up some stairs. The height of these stairs is 6 meters and it takes you 3.5 seconds to go up the stairs. Let's solve two problems. First, your output in watts, and second, how much energy did it require? Okay, so there's the formula for average power, which is equal to work over time. Now we have the time, 3.5 seconds, but we don't know how much work he did. And the work formula is FD. There's a lot of formulas to remember. If you want a free formula cheat sheet, go check the description. Anyway, you are working against gravity. So the force would be mg and the displacement is y. That means we can substitute in some values. So that means this is mgy over t. And if we sub it in our values, let's say you're 75 kilos and gravity is 9.8 and the height is 6 meters divided by time, you get this answer, 1260 watts. That's your output as you sprint up the stairs. Now here's a fun fact before we solve the next part of the problem, which is energy. 746 watts is equal to 1 horsepower, which is what car engines are measured in. Now in terms of horsepower, you have outputted almost 2 horsepower, which for a human is a lot. So this is a very high rate of work, which means that there's a lot of power. Next, let's solve for how much energy it required. So we know power is work over time. Since work is the amount of energy we use, we can rearrange for it and we get work is equal to power times time. We already found power in the last example, which was 1260 watts, and the time it takes is 3.5 seconds, which means that the energy required to perform this task is 4,410 joules of work. Now here's a tip when it comes to power and solving power problems, which I'll use in the next example. Power is work over time, right? And work is force times distance over time. Distance over time is equal to velocity. So you can rewrite power as force times velocity. So this is another formula for finding power. Here's our next problem. So you work at NASA and you're monitoring a Mars rover. And this Mars rover has a mass of 900 kilos and moves at a steady velocity of 2.5 meters per second. The acceleration due to gravity on Mars is 3.7 meters per second squared. Now your rover travels up an incline, up a little Mars bump. So our rover, let's say, looks like this. The wheels experience a rolling resistance force of 200 newtons. The incline is 15 degrees. So how much power is required to make this climb while maintaining this speed of 2.5 meters per second? Okay, let's see. So we're looking for power, right? And power is work over time. Or as we just figured out, force times velocity. So we just need to find his net force, and we already know his velocity, 2.5 meters per second. So all we're looking for is his net force in this direction, parallel to the incline. Let's see how much power he needs to overcome the resistance. So the resistance would be every force that's acting against him. Let's draw a diagram. Let's represent it with a box. Now here Fr is the resistance in total. The forces that are resisting his movement. First we have the rolling resistance friction, which is 200 newtons. And combined with that is the X component of gravity. Since if this rover was at rest, then gravity would probably start pulling it down the hill. So the X component of gravity on an incline is given with mg sine of the angle, which is 15 degrees. It's not cosine, remember, it's sine because we're on an incline. And I'll explain why in my incline video. So let's substitute our values. We have 900 kilos for mass, 3.7 for the gravity, and sine 15. The answer is 859.44 newtons in the opposite direction. So this is the amount of force that we must overcome to move up this hill at 2.5 meters per second. Let's find the power. So plug this number in here and plug this value for velocity. Put it into a calculator, you get roughly 2,648.6 watts of power. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.